Sure. My bad. Sorry about that. Okay. So what should I do? Should I start again? Or
okay.
It's okay. Sorry about that. Okay, so for those who are, so this is essentially this is the picture, and now about the energetics. Essentially, the energy of the body is determined by the state through a functional, and I will denote this by E hat. And this is a function of three variables, M and HS. And by the way, these two variables are constrained in the sense that the straight field HS has to be curve-free. This is the first condition. And the second condition is that the divergence of, let's say, this has to be zero. So this is the notation that we use. So the magnetization is defined on y of omega. And when I use this multiplication by the characteristic function, I essentially say that this is the extension, the trivial extension of the magnetization to the entire free. Okay, and this equation is called in the sense of distributions. So there is this constraint, and this energy has to be minimized by under these constraints. And this energy contains three terms. The first term is if you wish, the material term, which is the deformation energy, the magnetoelastic deformation. And this will be some function phi f of, let's say, x, gradient of y, and the composition between M and Y. Okay, so all these things live in the reference configuration. Then there is a contribution from the stray field, the magnetization energy. And this is mu naught, this is a constant over 2. And then we have the integral over R3 of the magnetizing energy. And then in addition, we have an external applied field, which we call dA or HA if you wish. Let's call this HA. And this is from R3 to R3 and has zero divergence. And this is the applied, is the magnetic field that is applied from the outside. And changing this magnetic field changes the energy landscape by a linear term. And this linear term is written like, okay, so this will be dx, this is xi, and then we have integral over R3 of m dot HA mu naught xi. I don't know if you can read it. Is it okay? Okay. So this is the general setting. And essentially, there has been a lot of mathematical work on this problem. In the standard setting of Brown, essentially the magnetization was constrained to be in the boundary of the unit sphere. So Brown would enforce this constraint that the norm of the magnetization would be equal to a constant, the saturation magnetization. So essentially, this energy would be plus infinity whenever the magnetization would not satisfy this constraint. And this is a non-convex constraint. So you can see that in general, the problem is not well posed and demands for relaxation. This is why this model has attracted the interest of many mathematicians. Back in the early 90s, there has been work by first, I think, James and Kinderlehrer, for example. Then also work by De Simone using Young measures. There is also some application in numerics. I have seen also a review paper by Martin with Prol, I guess, on the numerical treatment of micromagnetics and so on. A lot of work. And okay, but this is not what engineers have used. And what is important about this model is that it was originally developed to investigate domain microstructures. So the spatial level of resolution at which this model is, in a sense, is working is that of domain structures. So according to this model, if you add also an extra regularizing term, which depends on the gradient of M, the minimizer will develop like some sort of domain structures where the magnetization is essentially constant in each domain, and then the structures are separated by domain walls. Okay, so this is the setting for this model. But in the early, let's say, at the beginning of this century, which is now unfortunately more than 25 years ago, and engineers started to study other models for magnetoelastic bodies, which were essentially concerned with a new technology which was called magnetorheological solids. Essentially, these solids, maybe I can draw somewhere else. I think that if I just clean it, then it will be unusable, right?
Maybe you can use the other one, then the one.
But then, I think for the moment I don't need the slide. And this is just to make drawings, because I mean drawings on a PDF are not very good. Essentially, these magnetorheological elastomers are essentially elastic bodies which are realized by embedding magnetic particles, ferromagnetic particles inside a relatively soft elastic matrix. And the description, the scale of description of these objects is much larger than that of the single domains. So essentially, people were not interested anymore in understanding how we see this, the dependence of the magnetization of the particular point, because essentially the representative volume element in one of these bodies is much larger than the characteristic size at which that model, is considered. And so there is a manifold of papers about that. And essentially, the most important one, I would say, the first one is by Dorfman and Ogden. And 2004, essentially, more than 20 years ago. And they consider a completely different point of view. So instead of using the magnetization as the primary variable, the magnetization and the magnetic field, they use the magnetic induction. So if I make reference to that slide, so we have M, this is the magnetization, and then we have the magnetic field, H, which is the sum of the stray field plus the applied field, which is over there. Okay, this is the total the magnetization and magnetic field. The induction field B is defined as mu naught M plus H, the sum of these two. And essentially, in the model of Dorfman and Ogden, the primary, one of their models, the primary state variable, which would represent the magnetic state of a body, would be B instead of M and H. And this model has several advantages, because in a sense, it's local. The thing is that if you go back to this model I was showing you, you see that concerning the stray field, we can incorporate the curve-free condition on HS by using a potential. Okay, so if I say that HS is the gradient of some scalar potential, I can remove this condition, but then I'm left with this additional condition, which makes the model non-local. And this is what makes it interesting. On the other hand, if we consider this other model, essentially the only constraint that this B has to satisfy is that its divergence must be 0. And this constraint can be automatically incorporated into the model by introducing, let's say, a scalar potential A, so that the curve of A will be B. So that when I take the divergence, I will get 0. So in this sense, this model is local. And I will show you how this model is arrived at. So I think I can now begin with the presentation and with the slides. And okay, so this first slide is essentially a summary of what I was showing before. The important difference here now is that in a way I'm considering the deformation as given, because I want to show the equivalence between a model where because my variables of interest now are the magnetic variables. So you see that now in the energy, I have Y as a subscript. And also now I'm integrating the magnetic energy in the current configuration. So I'm pushing forward this integral in the deformed configuration. And so you have to redefine the energy, but you can write in that way. So we just consider the deformation fixed. And this is more natural because in a way, the Eulerian, we have been talking about this with Thomas as well, that the problem with these models is that you're mixing the Eulerian with the Lagrangian description. In elasticity, it's more natural to use the Lagrangian description, so to use a reference configuration, even though now people know how to bypass that. But the magnetic variable live in the physical space. So it seems more reasonable to work in the physical space, and this is why I introduced this reduced density. Okay, here I have slightly changed the definition. So here you have mu naught times HA. The product of mu naught times HA is the applied magnetic induction BA. Okay, so you can describe the external field either by the applied magnetic field HA or through the applied magnetic induction BA. They are proportional to each other, and they are both divergence free. Okay, so what about these two constraints? Well, essentially there is okay, so maybe I can erase this and wait it for. There is a geometrical interpretation of those equations, which I will show in the next slide. But essentially, the point is that let me go forward. So essentially, the thing is that if you have the magnetization M in L2. So it's easy to see that there exists a unique stray field HS, which is curve-free and satisfies this equation. And essentially, from the geometrical point of view, the stray field is the opposite of the projection of the trivial extension of the magnetization into the space of curve-free fields. So essentially, if you want to make a geometrical representation, so let's say that this is the space of L2 curl. So L2 curl of R3 is the space of all fields which are curve-free. So HS will be one of these guys. And the orthogonal complement will be the space of divergence-free fields. So this is just a geometrical cartoon, a geometrical representation. Okay? And essentially, let's say that the magnetization lives here. This is the magnetization
So maybe it goes on.
Okay, so is it okay now? I mean,
Yeah, I see you again. Yeah.
okay, you see me again. So as I was saying, essentially the magnetizing field, this HS, is essentially the field that is generated by the magnetization, and it's the projection of this M into the space of curve-free fields, which is HS. And essentially, the orthogonal complement of this projection, which is essentially
Giuseppe, you share the screen because
okay.
I see you, but we don't see you.
Okay. Can you see it again?
Yeah, good.
Okay. So what I was saying is that, okay, the orthogonal complement of HS here is what I call in the slide B sub S over mu naught. So B sub S is essentially the magnetic induction associated to the self-stray field. And the key point is that is this formula, which tells you that the magnetization energy, the demagnetizing energy, can be obtained through a minimum principle. Essentially, I can minimize, instead of minimizing over curve-free fields, I can compute this energy by minimizing over this direction, by moving over this direction. And essentially, the optimal B of sub S will be the one that is represented in this orthogonal decomposition. And this is the standard Helmholtz decomposition of fields in R3. So curve-free fields and divergence-free fields. So this BS will be an element of L2 div, and this is an element of L2 curve. And basically, this observation is the key to go from the, let's say, the MH-based formulation to the so-called B-based formulation. So to use B as the other independent variable. And this observation was, in fact, the first ones who made this observation, I guess, Stefan, were Pedregal and Jan, I guess. Even though they were not aware, at least what we are aware of, even though they were not aware of the significance of this auxiliary field that they considered. They just observed that that was the geometry. So this is a paper from Jan, and actually there are two papers, 2009 and 2010. And the idea is essentially, I think this is quite dense. I'm sorry about that, but the idea is expressed into this chain of equalities. So essentially, we start from the energy here, which is the energy in the MH formulation. So we had first the first integral is the integral of the, let's say, magnetic material energy, the material part of the magnetic energy, and the so-called Zeeman energy, the energy from the applied field. And then the energy of the stray field is computed through this minimization procedure. So I minimize this integral over the set of fields which I call BS. So the orthogonal complement of H into that space. And so the idea is that I can look at this as the result of a minimization procedure. So essentially, the idea is that you can mix the term. So you expand that square. So if I expand that square, I will have this BS square here. I will have an extra term here, and I will have this guy here, which is BA, the applied magnetic field, and the the applied induction field, and let's say the stray induction field. And the sum of these two is in fact the total magnetic field. And so I can introduce this auxiliary functional, which which I assume to depend on the, let's say, the B field. And then I say, okay, but if now I want to minimize this guy here, I'm essentially performing two minimizations. And I can somehow invert the order of the two minimizations. And I end up with a minimization over a field which essentially depends over of a functional that depends only on the magnetic state variable B. And the advantage of this approach, so I should, okay, I'm hopeless with this. So the advantage of this approach is essentially that the resulting functional is local. The key point is that when we minimize over the n variable here, so we have this chain of equations. So I assume that n bar and hs bar is a constrained minimum of the magnetostatic energy. So I've written the energy as this minimization. So I can minimize with respect to the m in L2, the minimization of this functional. I invert the order of the two minimizations, and I end up with this. At this step, when I have to minimize with respect to m, essentially I have something local that leads to essentially to a sort of convex duality, if you want. And this gives rise to the other to the new formulation. Let me see if I can move this up. Sorry.
Upper left.
Okay. That's very good. Thanks. Okay, let's put it here. It will do no harm. So essentially, over here. So essentially, if we assume, for example, that the energy psi hat, the original one, is convex with respect to the magnetization energy, then essentially finding the minimum, the optimal value of m will give you the minus the convex conjugate of this auxiliary energy psi, which is defined in this way. Okay, so this is the argument of this auxiliary functional. And at the end, you end up with the energy written in terms of this magnetic state B. Okay, so this is the argument by Pedregal and Jan. And what we have done with 7, when we began working on this problem, we were not aware of this paper. And okay, so when we found it, we realized that actually it was like relying heavily on convexity arguments. So essentially, this argument would work only in the convex case. But so in our work, we kind of extended the framework to cover also other cases of interest, like I will show you in a moment. Okay, so now. Okay, so in order to do this, essentially, I need to introduce the notion of magnetic critical point. So essentially, this is the Euler-Lagrange equation of the energy in the M8 base formulation. And I will skip I will not do the calculations, but essentially, if we go back to this energy and we compute the variation with respect to m, and we use the fact that Hs is a projection operator, we find that any stationary state, so any minimizer, has to satisfy this Euler-Lagrange equation inside the deformed configuration, where here you have the subdifferential of psi, and this works in the convex case. But the point is that this notion of stationary point can be lifted up even in cases where the energy is non-convex. This is the point. And there are examples where the energy, instead of being convex, is concave, for example. And the problem is still well posed. Okay, so by the way, this Euler-Lagrange equation can be interpreted as a sort of constitutive equation, because I remind you that this object here, so it's mu naught plus m plus hs plus BA. Okay, so if we this is equal to mu naught m plus hs plus ha, which is equal to mu naught m plus h. And it is exactly the B field that I was showing before. So this is B. And so this Euler-Lagrange equation is in fact can be interpreted as a conciliatory equation that says that the magnetic induction has to belong to the subdifferential of that energy, of this auxiliary energy, which is not the original one, by the way. Is the original one like augmented by this extra quadratic term, which is good because sometimes, even if this is even if this is not convex, this additional term may have convexifying effects. And of course, you can introduce a similar notion for the B model. So you may ask, okay, I have this energy in the B model, this E of B. And the question is, can I write the Euler-Lagrange equation for this energy? And the key point is that in this minimization, you have to take care of this constraint. Okay, so in order to do this minimization, you can incorporate this constraint using the indicator function of the constraint itself. So a function that is plus infinity when the divergence of B is not satisfied, and is this zero when the divergence of B is not satisfied. So you add the indicator function to this original constraint. And the point is that the subdifferential of this indicator function is made of all two functions, two vector fields, which are the gradients of something. And this is where these additional terms comes from. So the point is that if B is a minimizer of this energy, then this quantity here plus there must be some potential such that the sum of B minus BA belongs to this subdifferential. And essentially, this can be also interpreted as a conciliatory equation which relates the magnetization M with the magnetic induction. Okay, so let me go forward. And let me show you a very simple example. So the simplest example that you can come up with, it's not that taken from ferromagnetism, but it's just the standard linear relation between the magnetic induction and the magnetic field. In this isotropic case, so essentially the magnetic induction is proportional to the magnetic field through a constant, which if you are not in vacuum is different from mu naught. And if this constant is greater than the magnetic permeability of vacuum, then the magnetization aligns with the applied field, and the material is said to be paramagnetic. If this constant is smaller than the permeability of vacuum, the material is called diamagnetic, and the magnetization opposes to the applied field. And if you so what you can do, you can say, okay, I have the constitutive equations from that I have shown you before, and I can ask what is the energy that delivers that constitutive equation. And this is the expression of the energy, both in the M-based model and in the phi model. So you can see that in the paramagnetic case, this quantity is smaller than this one, and so this quantity here it's positive. Okay, but in the diamagnetic case, this is not, and in particular, the magnetic energy is concave. You can see this because if you look at this functional, you will see that this term is negative, but this does not compensate for the concavity. While on the other hand, the other model is convex. Okay. And the thing is that the diamagnetic case is not covered by the Pedregal and Yan framework. This is the point. Okay, so this is essentially a the situation. Essentially, the convexity and concavity are exchanged for the two functionals, and so this suggests that this equivalence is more about critical points and not minimizers. This is the point, because when one is convex, the other is concave, and vice versa. So if you want to characterize the equivalence, you should work at the level of critical point. This is the main idea. And in fact, this was Stefan's idea, Stefan's notation. So if you don't like it, I'm not the person to blame, but essentially you can treat both cases, both the convex case and the concave case, using a single notation, using a different notion of Legendre transformation according to whether the function is convex or concave. It's not complicated. You just change the sign to the function, and you take the convex conjugate, and then you change the sign again. This is basically the idea. And of course, these symbols now represent not necessarily the convex subdifferential, but could also represent the superdifferential, according to whether the function is concave or convex. And essentially, we have proven two theorems. So under suitable regularity and coercivity assumptions, essentially that the two energies, if you consider two critical points for the two models, essentially the two energy coincides. And this is a very important point to consider, that in the literature, there are many papers that consider the equivalence between these two models, but essentially, most of them fail to acknowledge that this equivalence holds only at the critical points, only if you are at equilibrium. Otherwise, the two energies do not coincide in general. And of course, you can also derive a proposition that allows you to go from the B model to the MH model and say that if I have a critical point of the B model, then the corresponding energy for the MH model derived through those constitutive equations that I was showing give a stationary point for the B model. And this is the other theorem, and says that suppose that I start with a critical point for the B model. I can define there exists a magnetization which satisfies this. This is a constitutive equation essentially that relates M with B. And once I know M, I can obtain HS by making this projection I was telling you before. And then automatically the projection satisfies this condition. It's curve free. And it also satisfies the divergence constraint, and this is a magnetical critical point of the MH energy, and essentially the key link between the two models is that is this one. So if I take these two fields obtained by that definition, and I compute this sum, I obtain exactly the B bar. So the passage from one model to the other is consistent with physics. And again, we have equality of energy. How much time do I have? Minus, it's negative or positive?
So 21 minutes.
21 minutes. Okay, very good. Okay, so another observation is that that one can make is that it is possible to, in the case when the energy functionals are smooth, essentially you can define the conjugate energies not by taking infima or suprema, but just by direct substitution. The point is that there are situations where the energy is not convex, but nevertheless, the gradient of the energy is invertible. For example, the typical case is when you have a saddle point. So let's say you have a function like this. So this is a non-convex energy. So suppose that this is our energy in a way. So you see that this is non-convex, but the gradient is invertible. And this makes it possible to define the kind of Legendre transformation even without resorting to minimization or to maximization, as I was showing before. And this allows for a generalization beyond convexity. And so with Stefan, we were looking for situations where, like exotic materials, where you can have, you can imagine, for example, a material that is paramagnetic in one direction and is diamagnetic in the other one. So in this case, the energy would be non-convex, but still the gradient of the energy would be an invertible function. And this falls within this setting. And so the key point is that only the invertibility of the gradient is needed, and that's all you need. And if you do that, you can rephrase the two theorems I was showing before. But in this case, you don't require the energy to be neither convex or concave. You just require that the gradient of the energy with respect to the magnetic variable, this could be B or M, is invertible. And if you do that, you can, in a way, rewrite the two theorems in exactly the same way. The only thing that you require in this case is that the energy has to be smooth, so must be differentiable everywhere. And this is the reason why in these two statements, instead of the subdifferential operator, now I have the gradient. Okay. And again, what you can show is that the two models are equivalent. So if I have a minimizer for the B model, I know what a stationary point for the B model. I can construct a stationary point for the MH model, and the two energies are again the same. And if I start from the MH model, I can go to the B model, and again the two energies are the same. From the point of view, if you look at the structure of the energy for the B function, let me go a little bit back, but I will talk about this a little bit later. So the advantage of this function is that essentially it's convexity in most cases. And from the point of view of engineers, this is a very good feature, especially for those who work, let's say, in homogenization. So there is substantial body of work in this direction. Let me just erase so that I have time to dry out. I will come to this point later. Okay, so let me give some other examples. So another example that you can consider is the one with the saturation constraint. So in this case, so essentially the saturation constraint tells you that the norm of the magnetization must be smaller than the saturation magnetization, and this is a relaxation of the constraint I was showing before. Okay, this is what comes out if you do the double Legendre transform of the energy. So if you do this twice, you go back to the convex envelope of the energy, essentially. And so if you look at the B model, the energy of the B model is minus the saturation magnetization times the intensity of the magnetic field B. And the constitutive relation that it's in fact the Euler-Lagrange equation of the functional tells you that the magnetization, that is, if B is different from 0, then the magnetization has the intensity of the magnetization is equal to the saturation magnetization, and the magnetization is parallel to the B field. If the B field is 0, you don't know much about the magnetization. What you know is that it has to be in the closed ball with radius the magnetization, the saturation magnetization. And this is in fact the subdifferential of the norm. And if you compute the energy in the other model, you get essentially a function which is minus mu a quadratic function if m is smaller than the saturation magnetization, and plus infinity otherwise. And this is non-convex, of course. Again, it's something which is quadratic. I mean, it's concave inside the unit ball. Well, it's not the unit ball. It's the ball of radius s, and then goes to plus infinity. Okay, and then another example I wanted to show is the. Okay, this is sort of constructed because this is the typical situation where you have a material. This is a situation where our framework applies. This is essentially an energy which is diamagnetic in one direction and paramagnetic in the other direction. The red B model would not work here, but if you work with critical points, then you can. Of course, because we are in the smooth case, and the gradient of these functions are invertible. Okay. So with 7, we were looking for examples where this is the case, and it looks like in some biological materials, you can have a different behavior in one direction and in another. So this is sort of a strong anisotropy. Okay, so I think it's a bit in advance of the time I had, but this is all I had to say, and I thank you for your attention.